Welcome back, friends. So, we have been discussing the summary of the discussions that we had in this course, wastewater treatment and recycling. In the last class we discussed the summary of the first half of the course from week 1 to week 6, and in this last class we are going to talk about the discussions. We are going to summarize the discussions that we had from week 7 to week 12. So, in the week 7 we did talk about the anaerobic biological treatment. So, week 6 we discussed about the aerobic systems in the activated sludge process, rotating biological contractor and trickling filter, those kind of stuff. In the week 7 we discussed the other type of biological treatment which takes place in anaerobic conditions. Now, anaerobic conditions, the microorganisms can break down the organic matter, particularly the biodegradable organic matter, into biogas, which is the methane and carbon dioxide, of which mostly it is like close to 60 to 70%, although it depends on the characteristic of the waste, but often with the domestic sewage we get 60 to 70% of the methane of the total biogas. Only little amount, less than 5%, goes to the sludge production. So, as a result the anaerobic system have lower biomass yield, okay, because the sludge production is low, and when the sludge production is low the biomass growth is low. So, obviously the nutrient requirement is also low. So, many times if there are like for aerobic system we had to supply additional nutrients if there is a nutrient deficient wastewater, but in anaerobic system we do not need to do that because the nutrient requirement itself is low. On the other hand, we cannot get nutrient removal also because nutrient requirement is not there. In some specific cases we do. So, we had the discussions further in the later weeks. So, then further these requires much less energy because we do not need aeration. It is an anaerobic system. So, there is no aeration, no requirement of energy for the aeration purpose, and the most advantageous part is that we can actually produce energy. It has potential to produce energy in the form of methane. This anaerobic decomposition of organic matter is a multi-stage process. So, there are 4 stages. The first is the hydrolysis, where the complex or undissolved form of organic matter is solubilized, okay. So, that converted to the less complex dissolved compounds. Then comes the acidogenesis, where conversion of hydrolyzed compound into the lower molecular mass intermediate compounds. So, various various volatile fatty acids or those kind of products are formed in here. Then the acetogenesis which actually uses these lower chain volatile fatty acids and finally produces hydrogen and acetate out of this, and the last one is the methanogenesis, which converts these acetate and at times even hydrogen into the methane and carbon dioxide. So, once it converts the acetate, it is called acetoclastic methanogenesis, or when it converts the hydrogen into methane, it is called hydrogenotropic methanogenesis. So, that is what happens in the anaerobic processes. Then the most common or most popular reactor configuration for this anaerobic wastewater treatment is UASB, which is upflow anaerobic sludge blanket reactor. So, this have a single tank system where the water is pumped from the bottom. So, it is a upflow system, water is pumped from the bottom and flows through a suspended sludge blanket. Now, the anaerobic bacteria which remains in this sludge blanket are responsible for breaking down the organic matter, and in the process they kind of transform it into the biogas. Now, this biogas is produced in the sludge bed, but since gas has a tendency to move up, so it actually moves up, and then after this sludge blanket we have a settling zone. So, because some sludge mass or some biological organisms also will come along with the gas particles, or water is flowing up. So, this upflow regime actually is responsible for the kind of ensuring the motion of the gas, like ensuring the mixing in the sludge bed itself. So, there is a gas motion, there is a upflow regime of the water movement. So, this ensures that enough amount of mixing is there and we do not need any mechanical mixer in the system. but due to this mixing, when the gas moves up or the water moves up, there are some biomass also moves up, and then we provide a settling zone where this biomass gets settled, and on the top of that there is a GLSS, which is gas liquid solid separator, which is responsible for the separation of all these elements. So, GLSS essentially, or the gas liquid solid separator, is a funnel kind of thing. So, it is if your, let us say this is your reactor. So, there is a deflector provided over here, then when water moves up, the gas will actually find a path and will be collected from this point onwards. The sludge particles, solid particles that strike this surface of the GLSS will be pushed back for settling, and water flows in the outflow here. So, it can separate the gas, liquid and solids, and that is why it is called GLSS, gas liquid solid separator. There are various other anaerobic systems. So, anaerobic contact process, anaerobic filters, the fixed film reactors and the fluidized based reactors are some of the other high rate anaerobic treatment systems which are used, but they are mostly used in the industries. Okay. In the domestic effluent, the very little application is there. Then we move to the week 8, where we discussed about the sludge management. So, when the wastewater treatment starts, so we discussed about the primary sedimentation. Now, the particles that are settling in the primary sedimentation, they are collected as a primary sludge. Okay. Then we discussed about the, particularly in the aerobic system, the activated sludge process, which is the most common biological treatment unit. So, in an activated sludge process, the secondary settling tank, which receives water from aeration tanks and let the biomass settle over there, some part is recycled, but a large part is wastage also. So, the amount of sludge which is being wasted or which is being generated in the secondary settling level is called secondary sludge, or we also call that as a waste activated sludge, because that is the sludge which is kind of being wastage from an activated sludge process. So, that way we generate these different types or different categories of sludge. Some tertiary treatment units may also generate little sludge depending on the technology used. Then the grit system also generates some grit materials, which is a kind of sludge, but that is processed separately, that usually goes to the landfill, because these are essentially the inorganic stuff with very high specific gravity. Whereas these secondary sludge or primary sludge has lot of organic carbon in this, lot of organic mass in this. So, around up to 60 to 70% of these sludges are actually the organic. So, wastewater sludge is perceived as a serious problem due to its high treatment cost and the risk to the environment and human health. The conventional activated sludge process have kind of the 50% of the total cost of the plant is attributed towards the sludge handling only. So, that is what is the importance of sludge handling. Usually the sludge is processed through a series of steps which involve thickening, stabilization, conditioning, dewatering or drying, and then disposal. There are few alternate processes like composting, co-composting or incineration for energy production is also kind of being used at few select places. So, that is the status of that way sludge. Now, if we see the typical water content of the wastewater sludge usually remains between 97 to 99.5%. So, that means there is very little solid content, and maybe for 1 kg of solid, if your water content is say 99%, so for 1 kg of solid we get a total mass of 100 kg, because 99% is water, just 1% is solid. So, instead of for handling just 1% solid, we have to process the 1 kg of solid, we have to process the total 100 kg of the sludge mass, because 99 kg is water, similarly that way. So, this makes it very difficult to processing, and that is why the first unit which is used is the thickening, sludge thickening. So, the gravity thickener or mechanical thickening devices like centrifuge or various filter beds are used for thickening purpose. Mostly the gravity thickeners are more popular. So, this is what is used, where water content of the sludge is reduced, and that is how we are able to reduce the sludge volume. we can reduce sludge volume as just to like around 90% also. So, if we are let us say just increasing the water content from say 1% to 4%, we are actually getting significant decrease in the volume even from this shift. So, the anaerobic digestion is the next process which is used for the stabilizing the thickened sludge. So, once we have done with sludge thickening, then we go for the digestion process, or we call that sludge stabilization process, and for this purpose anaerobic or aerobic digestion process could be used. Anaerobic digestion process are more common here because of high energy needs and high treatment cost with the aerobic digestion process, which is similar to activated sludge process, and we need to kind of give a larger retention time. So, aerating that thickened amount of sludge, oxygen transfer also becomes very difficult, and doing that for a large number of days is very difficult, very costly. So, that is why anaerobic digestion is far more popular. The anaerobic digestion actually uses the concept of anaerobic decomposition as we discussed in the week 7. So, and week 8. So, all those processes like the hydrolysis, acetogenesis and methanogenesis will take place, and eventually the 40 to 50% of the organic content of sludge is reduced to biogas. So, it gives a potential for producing biogas also, and that way making the process self sustainable. The next step is usually conditioning, which is optional. Many like for better dewatering characteristics, sludge is conditioned, and this conditioning can be done through by adding chemicals. So, flocculant using ferric chloride or alum or various organic polymers are used, or the thermal or heat treatment is used, but the heat treatment is far more costly, and the other way we have to have a higher chemical footprint. So, we have to make a choice that which one is the better option for conditioning, that is done for improving the dewaterability of the sludge. Then this digested sludge is usually dewatered in sludge drying beds or mechanical units. So, like centrifuge, filter press, screw presses are there which are used for the sludge dewatering, but the most popular or most common is the sludge drying beds, which is most simple also. So, here the sludge is laid on a drying bed, and we have under drainage systems. So, the evaporation takes off some water, and the percolation through that sludge bed, or the kind of percolation of water and collecting it through under drainage system is the other mechanism which two work simultaneously. The major removal is through evaporation, and because that works for a larger period of time. However, there is a large land footprint of the sludge drying bed. So, that is what is the like a problem, particularly when you have to put systems through in a limited area in a say dense population cities, where the area getting a large area is a big issue. So, one can actually go for the mechanical units for the sludge dewatering. Then the sludge hygienization, which is achieved through composting, lime treatment or pasteurization, could also be used, especially for its agricultural and landscaping applications. The sludge could be incinerated for utilizing its calorific value for energy productions. However, we have to cautiously evaluate the net energy footprint of the sludge, because for the purpose of incineration we have to supply also lot of energy, and what net energy gains are there, that needs to be properly estimated beforehand. As a final disposal, the dewatered sludge can be placed in sanitary landfills or can be dumped into the oceans. Reuse options are also coming up. So, reuse of the composted sludge in agriculture as fertilizers or in landscaping is also gaining popularity. At few places it is being reused as a building materials as well. Then the week 9 we discussed about the advanced or tertiary treatment options. So, the secondary level of treatment are effective in removal of BOD and TSS to adequate degrees. So, around 85 to 95% of BOD and TSS removal could be achieved, but this is still not sufficient if we want to use the water for reuse purpose, or we want to meet the discharge norms. So, for the purpose of meeting discharge norms or reuse requirements, we may need to further process the water, which is done usually through the tertiary or advanced treatment options. These targets the removal of residual nutrients, the fine suspended particles, the dissolved ions, metals, recalcitrant or non-biodegradable organic matters, then emerging contaminants, pathogens. Those are the kind of things which are targeted for removal in the advanced stage of treatment. For removal of nutrients, we have the biological as well as chemical processes. The biological process for nitrogen removal includes nitrification, denitrification, which is the most popular method, where the kind of through a process, sequential aerobic anaerobic process, the nitrogen is removed. So, first step is the aerobic, where the nitrate where the ammonical nitrogen is converted into the nitrate, which is called nitrification, and nitrite is the intermediate step here, and then the nitrate is anaerobically reduced to nitrogen gas, which is called denitrification, and which takes place in an anaerobic environment. Relatively recent technology in the form of NOx has also been developed and is getting more popular. The advantage with NOx that it transfers the ammonia and nitrite directly into the nitrogen gas. So, the requirement of say aerobic system with aeration for converting ammonia and nitrite to the level of nitrate is removed. So, just with a partial oxidation we can maybe convert ammonia to nitrate or ammonia itself, and then we can directly convert that into the nitrogen gas in anaerobic system. So, NOx is also done in an anaerobic system. There are chemical ways in which the air stripping can be used, or this is also called ammonia stripping. So, it effectively removes ammonical nitrogen by stripping off. So, what happens when the pH of the system is raised, we can add lime or those kind of thing for raising the pH. So, pH of system is raised, so ammonical nitrogen converts into the gaseous ammonia phase, and then that gaseous ammonia phase could be stripped off just by simple aeration or air stripping. So, that is what is the chemical approach. For the removal of phosphorus, there are biological techniques which kind of takes the advantage of a certain species which are called polyphosphate accumulating organisms or PAOs. So, they assimilate large quantities up to 20% of the phosphorus within their cells, and so this kind of organisms could be used for phosphorus uptake from the water. Then phosphorus can also be removed chemically through lime based precipitation or alum flocculation, where the phosphorus is converts to hydroxyl apatite or alum phosphate respectively and gets precipitated. There are sedimentation added with filtration in the presence of certain coagulants. Okay, so can be used for the removal of various small particles which generally do not settle in the primary or secondary sedimentation. So, if there are very small particles or colloidal particles, we can coagulate them using standard iron or alum coagulants and then make them settle in a sedimentation basin or filtration basin, or the combination of both. There are various heavy metals which could also be precipitated as metal hydroxide by just raising pH. So, at higher pH the solubility of these metal hydroxide is very low. So, many of these metal hydroxide like iron, nickel, copper, those kind of metal hydroxides, when we increase the pH through adding lime or NaOH solution, they get precipitated, which is called chemical precipitation. There are certain metals, for example arsenic, they could be removed through co-precipitation. So, for these what happens that we can add alum or iron coagulants, and when their hydroxide flux is formed, so the arsenic or these kind of things may get adsorbed onto the surface of these metals. So, these flux of alum or iron hydroxide flux, so since they get adsorbed onto the surface of these flux and these flux settle, so these metals also settle, also precipitate along with these flux, and that is why it is called co-precipitation. Then there are adsorption, which is a mass transfer process which involves the accumulation of pollutant at the surface of the adsorbent. Mostly activated carbon, either powdered activated carbon or granular activated carbon is used in the wastewater treatment, but it is more common for industrial scales. So, adsorption process is able to remove the various micropollutants, non-degradable organics and some metal from the wastewater. We also discussed the ion exchange process, which could remove the dissolved ionic impurities and hardness. So, how ion exchange works? It basically the target contaminant ion is swapped with another ion which is non-objectionable or much lesser objectionable, but of similar charge. So, there are ion exchange resins which has a polymer backbone and there is a functional group attached along with the ion is attached when it is water exposed to that. So, the contaminated ion in water comes attached to the functional group and the pre-attached ion less toxic or less contaminant ion is released back into the water. So, that is what is ion exchange process. Both of them have certain limitation in the form of both ion exchange and adsorption in the form of like their capacity can get exhausted. So, they need to be regenerated and then how many cycles we are going to regenerate, all those things are there, and then there are issues with the sort of interfering ions. So, interfering ions or interfering agents are there. So, if there are such things which preferentially gets adsorbed over the target ion, so then the efficiency will be decreasing of these systems. Then there are advanced oxidation process which are normally called AOPs, which targets oxidation through the highly reactive OH radicals. They used to treat the wastewater having recalcitrant organic, okay, and they can actually be used to either treat water either to complete mineralization level, but that is quite expensive because we have to ensure the full level complete oxidation of the compounds, and for that level of OH radical production and supply has to be ensured, or we can use this as a pre-treatment because these processes are known to increase the biodegradability, enhance the biodegradability. So, if there are recalcitrant organic compounds, they can sort of break them down to biodegradable compounds, and from there onwards the standard biological process will take care of that. So, that way this process could be used as a pre-treatment as well. Then there are membrane processes which there are microfiltration, ultrafiltration, nanofiltration, reverse osmosis, those kind of membrane process which are most popular membrane systems for water purification. So, these are perceived, particularly the RO systems are perceived as the most advanced treatment options which can separate almost all pollutants, okay, and produce pure water even for the potable uses. However, the processes are quite expensive and highly energy intensive. Okay. There are cross flow membrane modules like hollow fiber and spiral wounds. So, these are more popular than the dead end membrane modules because they have lesser fouling issues, which are one of the most critical maintenance aspect of the membrane system. Then depending on the need, we can go for disinfection. If the requirement is for disinfection, we can go for chlorination, ozonation or UV light based disinfection, which removes the pathogens. Okay. Then the week 10 we discuss the alternate wastewater treatment system. So, several systems configured differently than the traditional systems could be also be used, and they are in fact getting more popular because of certain distinct advantages over conventional system. These advantages could be in terms of better treatment efficiency, lower cost, ease in the operation or maintenance, and one of the feature is the compact design of these systems. So, there are wetlands constructed or artificial wetland, there are which kind of simulates the natural wetland systems. So, they use the power of wetland vegetation for the purpose of wetland vegetation, then adsorption or those kind of thing. So, soil microbial systems, everyone is assembled in a constructed wetland system. These are low cost and low maintenance systems, okay, which utilize these natural processes for treating wastewater, but they need a large area, and that is how their application is restricted, particularly in the heavily populated urban areas. There are sequencing batch reactor, which are another popular and compact design, where the typical activated sludge process are operated in the batches. So, these batches are sequenced through a series of treatment stages. So, we first fill, then kind of allow it to react, then make them settle, then decant, and then again keep it on static and go back to the refill system. So, that happens in a sequencing batch reactor. So, these systems are although energy intensive, but result in higher treatment efficiency for solids, BOD as well as nutrient removal. then either conventional activated sludge process or SBR systems could be augmented with the biofilm carriers, and then biomass growth takes place on these surface of these inert media which acts as a biofilm carrier, and as a result the biomass growth. So, we get the advantages of both suspended as well as the attached growth systems. So, these are done in a moving bed biofilm reactors, which is MBBR. So, in an activated sludge process, if we just put in these biofilm carriers, we will get an MBBR, or sequencing batch biofilm reactor. So, in a SBR system, if we add these biofilm carriers and biomass growth on the takes place, biofilm growth takes place on the surface of these carriers. So, we call that system as SBBR, which is an upgradation of SBR system that way. Okay. So, these are relatively known to enhance the system performances. There are another highly efficient and compact alternative treatment system in the form of membrane bioreactor that exist. So, it actually combines the suspended growth biological treatment systems like ASP with the submerged or external low pressure membrane systems for solid liquid separation. So, the biological process takes place of the degradation of organic matter, whereas the membrane is, instead of going for secondary settling basin, the secondary settling basin, because of the lesser efficiency, we use a membrane which gives us a better filtered quality. So, the requirement of tertiary treatment could also be omitted here, depending on the reuse application, or if needed we can directly go for a high end tertiary treatment stages. So, that way the MBR system works. They are quite costly, have high operation and maintenance cost also, but otherwise the efficiency is very good. The major problem is the complexity of the membranes and membrane falling. So, in the week 11 we discussed about the wastewater reuse and recycling, the basic aspect. So, release of the untreated or partially treated wastewater into the environment leads to the water pollution, and as a result deterioration of the freshwater resources, and as we are already under the qualitative and quantitative stress, our water resources are under qualitative and quantitative stress. So, this kind of enhances the problem further. So, wastewater recycling is considered as one of the most effective solution that helps in the pollution control of the natural resources as well as serve as an alternate water resource. So, this reuse and recycling could involve indirect or direct reuse. Indirect reuse means augmenting water resources, either groundwater or surface water resources, whereas direct reuse is using reclaimed water for specific targeted domestic, industrial or irrigation applications. The water reuse is preferred after adequate level of treatment. However, at few places the untreated wastewater components like grey water is directly reused without treatment for some uses like irrigation in horticulture or even for toilet flushing, but again there are certain risks associated, as we discussed during the week 11. Then if we see the like reuse and recycling aspect, the different type of wastewater including grey water, sewage, industrial effluent, storm waters could be reused or recycled, and we can use this reclaimed water for a large range of applications in the agricultural, aquaculture, urban or municipal sector, industrial sector and environmental sectors. Okay. The reuse of wastewater projects should ensure the protection of public health and environment, and follow the national or international regulatory guidelines. So, international like WHO has put through certain regulatory guidelines for wastewater recycling system. There are few countries which have own separate regulatory guidelines like USA and those other countries. So, they have their own separate guidelines for wastewater reuse. The decentralized systems are perceived better for local scale recycling, that is because we get saving in terms of cost and times by not going for long distance transport of the sewage, which is requirement of a centralized system. In centralized processing we have to basically collect the sewage from each part and then bring it to the far off point, and since this transportation things goes off, so we save lot of cost, transport cost and time. So, that is why it is perceived better, but it will be better if there are kind of appropriate reuse options are available in the vicinity. So, and furthermore, there is a feasible scale of decentralization should be worked out for optimum benefits, because decentralization can be done at a different scale, even from household to household scale, but that probably is going to be very difficult to manage and operate. So, instead of going for that level of decentralization, we should work out the optimum level of decentralization for the best benefits. Then this particular week we had discussed about the decision making and various current practices adopted in the water and wastewater recycling systems. So, water reuse and recycling is increasingly getting more popular across the globe, but there are some technical, social and political, financial issues that exist. So, like there are technical issues in terms of the complicacy of the system, treatment options, engineering reliability, then the financial issues in terms of the cost of the system, then social and political issues in terms of the public acceptance, political will or trade barriers. These are the major challenges that affects the universal applications of the recycling systems. So, several technological and management aspects of this wastewater recycling and reuse is being investigated, and the current breed of scientists and researchers are taking care in order to kind of develop more sustainable and robust wastewater recycling and reuse solutions. Then there is a concept of fit for purpose is gaining popularity, where the wastewater treatment schemes are selected based on the reuse option, so that the treatment is accordingly provided for the reuse option. So, we avoid over treatment or under treatment, and that way achieve the economic efficiency and environmental sustainability. So, for say some water, if it to be used for agricultural application, it does not need the complete removal of nutrients or treating it to the RO level, which is going to be very costly. So, that way we just treat it to the requirement for the irrigation water, and those kind of concept are referred as fit for the purpose treatment. Then due to the availability of number of alternative treatment process and various reuse opportunities, the decision making in this recycling project is becoming an important challenge. So, for this purpose, a decision support system which can guide based on the evaluating different alternatives under the given constraints, that which one is best. So, which can guide and help in decision making system. So, that kind of decision support system have a lot of value in the wastewater recycling domain. The public acceptance is another very critical barrier in implementing recycled water schemes. Okay. There are especially for potable uses, there are both success and failure stories. So, we have had several projects, wastewater recycling projects being stopped in the countries like USA and Australia for this public opposition. So, this becomes a major consideration for wastewater recycling project. So, towards the end of this, we discussed about the kind of global practices, and Israel is actually the world leader in the field of wastewater reuse, where over 85% of wastewater is treated and reused mostly in the agriculture. If we talk about the industrial and domestic uses, so Singapore's New Water is a very shining example of wastewater recycling system. We have another examples from the Orange County, California, then the Florida in the United States and many other places. In India, things are just catching up. So, we have like the awareness is increasing, but still we do not have a great recycling system in place for the wastewater treatment and recycling at multiple stages. Although there are some like small scale systems exist, the industries are being forced to adopt for zero liquid discharge policies, which kind of ask for the complete recycling of the industrial effluent, but from domestic sector it is still not that attractive. So, this is all that we discussed during this entire course. So, I hope that this discussion would have been fruitful for you, and thank you for being with us for this entire 12-week duration. Okay. I am open to your feedback, comments, queries in the forum. So, if you have any, please post in the forum. although the discussion here has ended, but we will be happy to respond to those queries or those concerns in the forum. I will be happy to have feedbacks also. So, we end our journey here for the time being, and thank you for being with us. Thanks.